Okay, briefly talking about buffers. Definition of a buffer basically is a solution that can resist pH changes upon the addition of small amounts of acids or bases. Okay, so this is the definition in a nutshell. And again, if you're just interested in a fruitcake. Sorry about that. So again, what I was saying is if you just want to skip to the calculations, go for it. But the definition of a buffer is something, so generally speaking, some solution that can resist a major pH change. If you add in a little bit of proton or add in a little bit of hydroxide, it manages to not change its pH significantly. There's reasons for that, which we're going to get into. The reasons have to do with the composition, so what is in a buffering system. A buffering system needs to contain a conjugate acid and base pair in similar and pretty significant molar amounts. So we're not talking about like something times 10 to the power negative 10, okay? We're talking about maybe a 0.1 mole per liter acid and a 0.1 mole per liter conjugate base partner, okay? So best way I think to do this is with an example. So let's look at a buffering system. I'm just going to make one up here, okay? So I've got acetic acid, okay? So let's say I have a 0.1 sig dig, not very many, but 0.1 mole per liter solution of acetic acid, okay? And then I'm going to mix that with a 0.1 mole per liter solution of, actually let's change this a little bit, okay? I'm going to make this a 0.15 mole per liter solution, and I'm going to add another sig dig to up here, okay? So I've got a 0.10 mole per liter acetic acid solution. I've got a 0.15 mole per liter solution of sodium acetate. Why sodium acetate, you might ask, okay? Well, what I want to, so obviously this is a, this is a weak acid, weak monoprotic acid. I want to get a conjugate base partner for it in the same solution in equivalent stoic, molar amounts, okay? Not stoic, there's no reaction here, but molar amounts, okay? So I'm looking to get in this acetate anion, okay? You can't just put in acetate anions by themselves. They always come with a cation, right? So you're going to take some of this entire soluble ionic compound, dissolve it in solution to end up with this concentration to give you a conjugate base partner to this acid, okay? And I'm not really concerned about the sodium and what sort of impact it's going to have on an equilibrium system or on a pH value, because we've talked about that already, okay? So the system that we're looking at then is, I'm going to abbreviate now, HA, okay? The system that we're looking at is this, okay? I'm going to calculate, so I'm going to put in a question here. What is initial pH of the buffer? Because the best way to explain buffer action is to see it, I think, mathematically. So the initial buffer pH value I'm going to get to with an ice table. So I have 0.10 mole per liter of my acid. I've got a 0.15 mole per liter acetate that came from that sodium acetate. 0 because I'm disregarding autoionization of water. It's going to shift to the right like so. Okay. I'm going to look up the Ka value of acetic acid. It is 1.8 times 10 to the power of negative 5, so that goes along with this buffer solution, okay? So I'm going to set this ice table up to my Ka to get my pH. I'm going to disregard both of these because of the 100th rule, okay? So I'm going to have my 1.8 times 10 to the power of negative 5 is equal to 0.15x over 0.10. I'm going to solve for x, which is my proton concentration. So I'm going to have my 1.8 times 10 to the power negative 5 times your 0.1 divided by your 0.15 is 1.2 times 10 to the power of negative 5 moles per liter. Kick that over to a pH value. I get a pH value of 4.92. This by itself is relatively meaningless, okay? What I want to see though is how this buffering system that I've created, and I now know the pH value for, can resist a change to this pH value when I add in some protons or maybe add in some hydroxide, okay? Okay, so part B of my question is, what is the pH after 0.010 moles per liter proton forms in the buffer? Okay, what I mean by forms in the buffer is we're not considering any volume change that might accompany this. Now, technically, there will be a volume change. It's not just magically appearing, but we're disregarding that, okay, just for simplicity for this year at least. So I've added in some acid. So just like titration, I want you to consider this as two parts. You're going to think about the stoic, okay, and then you're going to think about new stoic determined concentrations jumping into an equilibrium system, okay. So when you add acid, the part of the buffer that's going to consume that acid is the basic part. So remember, you have your acetate anion, which is the conjugate base of the weak acid, acetic acid. This is going to react with the proton that you put into the system quantitatively to form acetic acid. Okay, it's an acid-base reaction. So a unidirectional arrow, this is a stoichiometric reaction. Again, we're considering the stoic, even though it's not entirely correct, it's good enough for us. We're considering the stoic independently of the equilibrium system and dealing with that first, okay? Now what I've just plugged in here, now this is not an ice table, this is me still dealing with stoic. I plugged in from the previous slide the concentrations, initial concentrations of acetate and acetic acid that I had in my buffering system. Now, really, I do have equilibrium concentrations from my buffer system itself, but remember, we disregarded the X, okay? We can, and the textbook doesn't do the greatest job of explaining this. What I'm using for my stoic are really my initial concentrations, but because X was small enough for me to disregard, that's good enough, okay? So don't worry about calculating and plugging into your stoic equilibrium concentrations. We're going with initial, but again, it's because of the small x situation, okay? So again, not a nice table, this is stoic. I am adding in 0.010 moles per liter of proton, okay? It's going to have a stoichiometric reaction with the base. So this is stoic. They're in a 1-to-1 ratio. So this proton is limiting, so that's going to be used up, okay? 0.010 moles per liter of proton is going to use up 0.010 moles per liter of your acetate. So this is comparable to what we did in titration. The number of concentration, okay? We're using concentration values for stoic, but that is totally okay because again, we can just assume that this is all happening in a 1 liter solution, okay? So we don't have to kick things over to concentration. So the concentration then of your acetate that remains will be 0.1, let me get this right, 4 moles per liter, based on your 1-to-1 reaction with that acid and the fact that the acid consumes some of that acetate, okay? Now looking over at this guy here, I have 0.10 moles per liter already in my buffer. Again, we're disregarding that X from the preceding slide. As my acid is consumed by the acetate, it produces 0.010 moles per liter of your acetic acid. So I have a concentration of my acetic acid of 0.11 moles per liter. Okay, so again, make sure you understand this. You have an acid-base reaction. The acid is limiting, okay? It's going to consume some of the acetate, which is your base, and produce some acetic acid, okay? And these are your new concentrations after that quantitative reaction with the protons that you've added to that buffer system. Okay, now these guys are going to hop back in. I'm going to do it up here in blue. Hop back into this equilibrium system. Okay, as your new initial concentration. So I'm going to plug in 0.14, that's a concentration, okay, and 0.11 and 0 because you've consumed all of your acid here, okay, because it was limiting, and you're disregarding the autoionization of water. So you're going to have 0.1, so this is my ice table, so this is my equilibrium, okay, minus x, I have x, and I have 0.14 plus x. I'm just squeezing it in here, okay? Just like before, we're going to disregard these small x's. We're going to set it up equal to, I'm just kind of putting a box around this, equal to my Ka, which was 1.8 times 10 to the power negative 5, I think and hope. I'm going to have 0.14 x over 0.11. I'm going to solve for x and kick that over to a pH. I'm doing that as we speak. I got 1.4 times 10 to the power negative 5 for my protons. Take the negative log of that. I get a pH of 4.84. Okay, now you can see that a buffer actually works, right? Because look at, if you want to go back and look, if you don't believe me, but on the preceding original buffer pH calculation, it's not significantly different from what we just calculated, even though we added acid. Okay, so the acid that we added was consumed by the basic part of that buffer system. Okay, it does change the pH a little bit because now you have relatively more weak acid than you had before compared to the base component of that buffer system. So it does change the pH a little bit. It's a little bit lower, but not substantially. Now another question is to explain something that's not a buffer and what impact adding proton would have to something that's not a buffer. Think about water. At 25 degrees Celsius, there we go, the pH of pure water is 7. And that's because at 25 degrees Celsius, the proton concentration is 1.0 times 10 to the power negative 7. Kick that over to a pH. That's where this value comes from. If I added 0.0, If I added 0.01 mole per liter proton to a water solution, then the pH of water would change significantly. The pH value would essentially be the negative log of the 0.01, because even though 0.01 is a pretty small concentration of proton, it's still way bigger than what's going on with the autoionization of water, right? So then this proton concentration really overwhelms the equilibrium system, and if I calculate the negative log of 0.01, I just plugged that into my calculator, shameful. The pH is actually 2. So the pH changes from 7 to 2 with the addition of the same amount of proton that you added to the buffer system. Okay, so in that buffer system, you're talking about less than 1 pH unit worth of change when you add in that amount of proton. In pure water, that's a 5 pH difference because water is not a buffer. Water does have conjugate acid-base pairs in that system, but not in comparable quantities, right? So you can pick out conjugate acid-base pairs of any equilibrium system, but unless they're present in relatively similar and pretty significant molar quantities, it doesn't have the ability to consume small amounts of proton or small amounts of hydroxide that you add. Now, you'd have the same sort of situation if you added hydroxide, but it would be the acidic portion of the buffer system that would stoichiometrically react with the hydroxide, and you'd go through the same process.